Hello all, in today's session let me learn about how to design a synchronous counter, which is a up counter as well as your down counter. In last session we learned about ripple counter. What are the drawbacks of your ripple counter? Let me discuss that. Thereafter I'll move to your designing of synchronous up counter and design as well as your designing of asynchronous down counter. So asynchronous counters comes under a serial counter since we don't have a common clock pulse which can clock here simultaneously all the flip flops. So here the preceding stages can act like a clock for your next flip flop. So since that, there was a large time delay introduced in your asynchronous counter due to that unsymmetrical nature of your clocking of your flip flops. So you could have your propagation delay is more in your asynchronous counter, and they are little bit slower devices when you compare with your synchronous counter. But it is easier to design, so hence we were preferring here if that speed is not an important criteria, then we were going to prefer the asynchronous counter. Whereas synchronous counter, since you have a common clock which can clock your all the flip flops simultaneously, so since that, it depends on the speed of the synchronous counter depends on your clock frequency. So we could achieve more speed than your asynchronous counter. So somewhat it is difficult to design, but we were going to prefer synchronous counter. So since all the flip flops are synchronized with or controlled with the triggering signal. So now we move to the synchronous counter design, and the other drawback in a synchronous counter is, so if you are taken a clock frequency with the high frequency signal which is applied on your first flip flop, so because of that unsymmetrical nature of your clocking your every flip flop, so few states are missed in your asynchronous counter due to that propagation delays of your each flip flop. So if that frequency of your clock is very high, so a few of the states may skip in your asynchronous counter. So since we are going to the synchronous counter, so where all the flip flops are triggered and controlled by the common clock signal. Now let me move to the designing of your synchronous counter up counter. Later we'll move to your synchronous down counter. So before we were going to that, so we can prefer any type of flip flops here. So preferably we can use your JK or T flip flops, so or else you can prefer your any type of flip flop. But whereas in a synchronous counter, so you can prefer only the toggle flip flop or your JK flip flop to design your asynchronous counter. So now here in your synchronous counter, the flip flops can change its next state upon having the clock transition on your clock signal. And one more thing here we need to discuss that each flip flop which are taken, which is either SR or D or your JK or T flip flops, all are edge triggered flip flops. Now let me move to designing of your 2-bit synchronous counter. Before we were moving to that 2-bit design synchronous counter, so we have to follow some procedure steps to design a synchronous counter. So in order to design the counter, so we have to follow some procedure step. The first one is finding the number of flip flops. So now it depends on your counter how many bit counter it is. So if it is a 2-bit counter, you have to prefer the number of flip flops to be used is 2. If it is 3-bit, so each flip flop can hold only 1 bit of data. So if it is a 3-bit counter, you have to prefer the 3 flip flops of JK or 3 flip flops of T or 3 flip flops of D or 3 flip flops of SR. Next, if it is depends on your number of states, so here you have to follow some basic equation, which is 2 power n must be greater than or equal to capital N, where capital N denotes your number of states which is introduced by that counter, and small n denotes your number of flip flops to be used to construct your counter. So now if I want number of states are 4, so then n capital N is equal to 4. So in order to obtain that 4 number of states, this small n must be equal to 2. So hence the minimum number of required flip flops are 2 square, which is equal to 4. Hence it satisfies this relation 2 power n is equal to 4. Now 2 power 2 is equal to 4. So The minimum number of required flip-flops to design number of states are 4 is 2. In the same manner, to design a counter with the number of states are 8. So here let I introduce that small n is equal to 3. So then 2 cube is equal to 8. So minimum number of flip-flops to be used is 3. For example, if I require the number of states are 10, so this n equal to 3 is not sufficient, then hence I'll move to here n equal to 4. So now n equal to 4 is 2 power 4 is greater than your number of states are 10. So 2 power 4 is 16. 16 is greater than 10. So number of flip-flops required is n is equal to 4 to obtain your number of states are 10. Next, upon finding that number of flip-flops, we need to draw the state diagram. So state diagram will give you the what is the present state, what will be the next state if my present state is a particular state of S naught. So for example, my initial state if it is 0, so next state in your up counter must be incremented by 1. So 0, 1 is your next state. So the successor point is 0, 1 and the initial point of that will give you this arrow will give you the successor point is 0, 1. The initial point is 0, 0. So this initial state is called initial point is called as initial state or the present state. So the successor state is called as your next state. So 0, 0 is the present state, 0, 1 is the next state. So if my present state is 0, 1 in your 2-bit or your 2-bit counter or your 4-state counter, so your next state is 1, 0. If my present state is 1, 0, so next state must be 1, 1. If it is a 4-state device, sorry, 2-bit counter. If my present state is 1, 1, next state must be 0, 0. So this will give you the state diagram. So which will give you the detailed state transition from one state to the other state. Upon drawing that state diagram, we need to draw the excitation table. In that excitation table, you should have your present state, next state. In order to obtain that state transition from present state to the next state, what are the excitation inputs required, that we need to find it. So upon finding the each excitation input, we have to find the minimal expression of each excitation input, and then we are going to draw the logical diagram. So these are the basic steps to be followed to design any synchronous counter. Now first step we'll follow here. We will need to design, the given problem is 2-bit synchronous up counter. So to design this, so as they have given 2 bits, so each flip-flop can hold 1 bit of information. 2 flip-flops are minimum number of flip-flops required is 2. So hence small n is equal to 2. So we require 2 number of flip-flops, and the problem itself they have given JK flip-flop you have to use. So we have choose that flip-flops are JK flip-flops. So 2 JK flip-flops to be used, and then we draw on the state diagram of your counter. So what is the initial state, what will be the next state, what is the present state of 0, 1, next state is S2. If my present state is S2, next state is S3. Upon having S3, what will be my next state is S0 is 0, 0. So is your final state, so which you obtain here again come back after obtaining your final state, come back to its initial state which is 0, 0. So now upon drawing the state diagram, next we are going to draw the excitation table using your excitation table of your given flip-flop. So JK flip-flop excitation table is given here. 0 to 0, 0 don't care, 0 to 1, 1 don't care, 1 to 0, don't care 1, 1 to 1 which is don't care 0. So now as here I given that QB, QA, QB star, QA star, JB, KB are the second flip-flop inputs, and JA, KA are the first flip-flop inputs. So next here these are the QB and QA are the present state, QB star and QA star are the next states. So as here 2 flip-flops, so 2 outputs we have. So QB, QA are the present state, QB star, QBA star are the next state. So based on the state transition from present state bit to the next state bit QB, let me compare. Then we will find your JB, KB value 0 to 0. So 0 to 0 is 0 don't care from your excitation table. J input required and K input required is 0 don't care. Next 0 to 1 is 1 don't care. Next 1 to 0 is 0 don't care 0. So don't care 0. 1 to 1 is don't care 0, 1 to 0 is don't care 1. So 1 to 1 is don't care 0, 1 to 0 is don't care 1. So as I have been completed the first flip-flop excitation inputs. Next, second flip-flop excitation inputs are JAKE is calculated based on the state transition of QAs to QA star. 0 to 1, 1 don't care, 1 to 0 don't care 1, 0 to 1, 1 don't care, and 1 to 0 is don't care 1. Upon writing your each excitation input in terms of its standard SOP as the function of your present state, which is QB and QA. So I can write here sigma m of only one minterm is present on 1 and 2 don't case which is on 2 comma 3. Next, in the same manner, KB is written as a function of QB and QA present state as only one minterm which is on 3 along with don't cares are sigma m of sigma d of 0 comma 2. So next JAK is having two minterms which are on your 0 along with 2 plus sigma d of don't case are 1 comma 3. Next KA is also having two minterms. So here you have it on 1 3 along with don't case are sigma d of 0 comma 2. So now upon taking these expressions, let me prefer your k variable map. So in order to minimize your each excitation inputs, so using that two k variable maps or your 4 cell k map method, we found that JB equal to QA, KB equal to QA, JA equal to 1, KA equal to 1. So here only one. We used one don't care not to cover the midterm. So one pair. So QA. So QB is different for all these two midterms. So hence it is not comes into your product term. Only QA is logical one. Hence it is represented with QA. So KB also one pair we have. So QA is the common variable for these two midterms as I have used here. Don't case do not to cover your midterm one. So KB also equal to QA. JA is, so here to cover your two midterms I used your two don't case which can form a quad. Now in a two variable k map if I have a 4 midterms the function minimal function is logical one. So k is also equal to logical one. So now using these two expression and by taking your two flip flops we can design your logical diagram of your up counter. So now let I take your two flip flops. So JA, KA, JB, KB, A flip flop and the B flip flop. So JA is your least significant flip flop or the least significant bit and your B flip flop is your most significant bit flip flop. Now so let me draw the timing diagram of this. So we are going to have your a continuous square wave signal, so which is on negative edge triggered. So we have connected all the clock pulses of your two flip flops commonly together and connected to the clock signal or the trigger signal. So initially let me clear the states of your two flip flops to zeros. Hence, so before your first clock pulse the states of your QA QB is 0 0. Next, upon giving that first clock pulse, since J K are logical one, so this A flip flop is in a toggle mode, so hence it will obtain your toggle state on your QE, so which will be toggled from 0 is the present state, next state is logical one, and this state is continued till you get your next negative edge on your clock, so which is on second clock pulse negative edge. So next on second clock pulse negative edge, so your state will change from 1 to 0. Next on third clock pulse clock edge it will change from 0 to 1. Like this for every clock negative or the trailing edge of your each clock pulse, the state of your first flip flop or the LSB is or changing its state from 0 to 1 and 1 to 0 again 0 to 1. Now so the outputs of your first flip flop have been connected as your inputs to the second flip flop. So for the first flip flop, so previous state is 0 on your first clock edge. So hence JEB KB equal to 0. So it continues the same state as its next state in your second clock pulse. So while it is getting your second clock pulse edge, So then here the previous state of your QA is logical 1. So hence JB KB become logical 1. When these two are 1, the previous state of your QB flip flop will toggle from 0 to 1. And this state of logical 1 is continued till you have your fourth clock pulse negative edge or your trailing edge. So now on the third clock pulse, since my present state is 0, so it has to continue. The next state is also equal to logical 1. So on your fourth clock pulse, since my QA is equal to logical 1, so JB KB are equal to logic 1, and the state will be turning from logic 1 to 0. So toggle from 1 to 0. Now if I count here, so for the first clock pulse, so it has been counted as 0. One second clock pulse, it has been counted as 1 0. So in the third clock pulse, it has been counted the states on your QB as well as QA is logical 1. So which will give you the decimal codes has here 0 and here 1, then here 2, then 3. So next it comes back to its initial state upon your having your fifth clock edge, which is equal to the initial state, which is 0. So here 0 0 is the first state, 0 1, next 1 0 is the third state, 1 1 is the last state, and here so after getting the last S4, so it comes back to its initial state, which is S0 or your S1. So like this, so we can have your counting and up sequence. So just by observing here, the decimal codes are incremented by 1 or your binary codes are incremented by 1 after giving your 1 clock pulse. So it comes under your up counter. So this is about our today's session, up counter designing. In the next class, we were going to learn about the down counter design.